So yeah, awesome. I love watching launches and covering launches with you guys. It's really fun. It's really fun to do on my end, and hopefully you guys get to learn some stuff. So I do appreciate it. But stick with me. We still got plenty more stream. Let's see. What do we want to play? That shot was about 120 miles south, by the way, for reference. Nice. What's your thoughts on Super Heavy not using RCS and instead using ullage for control? That's a good. That's a really good idea, right? Yeah. I mean, so okay. Here, think about it like this. So here, we'll go back into space news here. Just real quick. I'm just gonna mark change category 2 times to mark the VOD here for drummer, so we can cut it down. So erudite tank ullage. So let me bring people up to speed. So Falcon 9 has nitrogen thrusters up at the top. They're nitrogen cold gas thrusters. And the thrusters that are on the top of Falcon 9's first stage that it uses for steering up on orbit and, in the final seconds of landing, basically is just a compressed nitrogen tank that's venting. It's like basically the gas that you use to clean your keyboard. Straight up, right? Super Heavy doesn't have anything like that. In order to make the rocket as simple as possible, but also be able to reuse the rocket and land it, you're still going to need some thrusters. Because remember, Super Heavy is going to try to get caught by the pad with the chopsticks. So you're still going to need something up there. Now, there are already gases inside of rockets' fuel tanks when they come down and land. Those are called ullage gases. Now, historically, for a rocket, rockets haven't been reused historically, right? Like no reusable Titan or Atlas or Delta rockets, right? So what tank ullage is used for in real life is basically replacing the volume inside of the fuel tanks as the rocket is going up, right? Replacing it with gas, so the pressure doesn't drop in the fuel tanks. The rocket engines need to be fed fuel at a pretty constant rate, because unless the rocket engine is throttling, right? Like it needs to be fed at a pretty constant rate, or else if you get like a pressure drop in the fuel tank, you're not going to feed the propellants correctly into the motor, and that can create all kinds of problems. So what the engineers in the 50s and the 60s came up with is basically put a pressure vessel inside of your fuel tank or somewhere on the rocket that pumps gas into the fuel tank as the fuel drains out to maintain a constant pressure inside of the fuel tank. Now, on top of, propellant feeding and whatnot, rockets use residual pressure inside of the fuel tanks for structural rigidity. Basically, the tanks in a rocket, when they're pressurized, makes the rocket a lot stronger. Think about like if you had a soda can, right? If you have a soda can and it's depressurized, you can press on it. Yes, this is from the other night. But if this thing was closed and pressurized with liquid inside of it, you could stand on the thing, and it's really not a big deal. Rockets do exactly that. They do the same thing. So you have to maintain a constant pressure inside of those tanks, and the gases that they use to replace the liquid fuel that's draining out of the rocket are called ullage gases. Now, on Super Heavy, the gases, the residual gases inside of the tank, right, are the reaction control system thrusters. Those are your stability thrusters. They're basically tapping off of the tank ullage on Super Heavy, right? So SpaceX is. Now, EJ, didn't you just say that you need to maintain the pressure? Wouldn't using those thrusters a lot make the pressure go down? Yeah, sure. Think about, so erudite, picture Super Heavy's trajectory in your mind, right? So let me, give me 1 second. Let me get some pictures up here. Picture Super Heavy, right? Staging. All right, so where do Super Heavy's ullage gases come from? Super Heavy is utilizing a phenomenon called autogenous pressurization. What is autogenous pressurization? What does that do? All right, so on Falcon 9, for instance, there are helium tanks that are inside of the fuel tank, and the helium tanks basically open up when the fuel starts draining. So they're pumping helium into the tanks. Why do they use helium? Helium's low mass. It's lower mass. It would take more work to move nitrogen up there than it would helium. Yes, rockets are engineered to that tolerance where a couple of extra kilograms, is like the difference between working and not. But not necessarily Falcon 9, but that's what they started with. So that's, you go with that's the other thing with rocket science. Go with what you know, right? So, yeah, and it's inert too. Exactly. Bingo. So, because Starship as an integrated system is designed to be able to go to like Mars and refuel on Mars, it's going to be a while before we figure out how to pull helium out of the Martian surface, or even if there is some trace helium like in the Martian atmosphere, that it's not going to be there. And then on the moon, that's going to be even more complicated. Long story short, helium isn't really readily available on Mars or on the moon or anywhere in the solar system. Heck, it's pretty dang rare for this planet too. But that's another story. So SpaceX basically went with the design decision to not use helium gas as ullage gases. The Raptor engines produce methane gas and oxygen and liquid and oxygen gas by themselves because of how they deliver fuel. So this is, once again, I'm not getting sidetracked. This is all kind of, you got to figure this out. So you have to explain this to understand why they're doing that. And erudite, I'm bringing everybody up to speed, and I'll get to the explanation here. So, okay, the Raptor engine uses what's called a full flow stage combustion cycle. I could go explain what that all means. Long story short, you have methane gas coming in, or you have liquid methane coming in and liquid oxygen coming in, and the rocket basically turns the rocket engine turns that with what's called a pre-burner. It turns the methane into gas and it turns the oxygen into gas. Why would you do that? Why would you do that? Well, the short story is that gases are easy to light on fire. They're easier to light on fire. Think about gasoline. Gasoline itself isn't flammable. The vapors are flammable. Okay? That's an important thing to understand. It's the fumes from the gas that catch on fire. Now, why is it the fumes and not the gasoline? Well, gasoline by itself doesn't have any oxidizer in it, so it's not going to do anything. Right? When gasoline evaporates, the gasoline turns into a gaseous hydrocarbon that combines or atomizes with oxygen in our atmosphere. And that's why the oxygen that's found on Earth, right? That's why gasoline's flammable. It's the it's the fumes. The atomization that just naturally occurs if you just pour gas on the ground, right? Hey, Van, 54-month resub. So, Raptor engines, long story short, in order to make a gigantic freaking explosion coming out the back, they take the incoming liquid propellants, turn them into gas, then combine them. And then blow it out the bottom to make an even more violent explosion. Yeah, you get better atomization when you're combining gas with gas. You can get more power that way, you can get more efficiency that way. Because you're getting better atomization. You're making better fumes. You're giving the liquid methane and the liquid oxygen the best possible chance to basically stick onto each other and explode. That's what atomization is. Like, oxygen likes to cling on to stuff, basically. Kaplach. Not like that. Oxygen likes to attach to things, especially hydrocarbons. That's just, I mean, chemists are probably going to slap me for saying it that way, but not a chemist, dude. We have to cook, Jesse. So getting better atomization, right, will make a bigger explosion. And with something like Starship, you're going to need a bigger explosion. So, because the rocket engines are already turning methane into gas before they blow it up out the bottom, and they're already turning oxygen into gas before they combine it and blow it up out the bottom, there's tap-offs. There's pneumatic lines that take some of the pressure from the pre-burners, right? And they basically send that up a pneumatic line right back into the fuel tank. So their ullage propellants are actually gaseous byproducts from the rocket engine. I can actually show you another vehicle. That SpaceX isn't the first ones to do that. SpaceX aren't the first ones to do that. There's a vehicle that existed that flew for 30 years that did the exact same thing to simplify its fuel tank design. Anybody know what that is? Oxygen is basically the chemistry version of Velcro. Mm-hmm. Yep. That's the space shuttle's external tank. The space shuttle main engines did the same thing because you're getting rid of the shuttle external tank. And nice truck. Because you're getting rid of the shuttle external tank every time, you don't want to fill this thing up with helium gas. That gets really expensive really quickly. So have the engines make the ullage gases for your tank to maintain pressure. You got to do that with the external tank because there are points in the flight where the external tank is basically your glue that's holding the SRBs and the shuttle together. The external tank is the primary structural carrier for the vehicle, right? Without the external tank, the SRBs they won't stay there. And without the external tank, the shuttle definitely won't stay there. So the external tank is just a structural piece, but they don't want to complicate the design by putting helium in it every freaking time. So they make the ullage gases with a part, the shuttle being on the back, the shuttle engines, they make the ullage gases for it with the engines because you get the engines back, but you don't get the tank back. Now, if you look at the external tank, you see this pipe that comes out the side here. That's called a LOX downcomer because the LOX comes down from the LOX tank down into the back of the space shuttle to feed the shuttle's three main engines. There's the hydrogen downcomer. The hydrogen downcomer basically works on a siphon from the bottom of the hydrogen tank. It basically takes takes a 90-degree turn, and there's a pickup at the very bottom of it. Now, everybody knows what those are. Everybody can see that right there, those pilot dowels are the bolt holes for where the shuttle bolts to the external tank, and this is the struts that hold everything together. What a lot of people don't know are those lines right there. See these two lines? See that? Those are the pneumatic repressurization lines. Those are the autogenous pressurization lines. One of those goes to the top of the hydrogen tank, and the other one goes all the way up to the top, to the very point on the front of the ET, because the nose cone on the external tank is also the LOX tank, the liquid oxygen tank. Shuttle was doing this in the 70s. Well, in the 80s, technically, but you get the idea. So this isn't a new thing to do. Now, the reason why the shuttle did it, once again, is because they're getting rid of the external tank. The reason why SpaceX is doing it is because they're trying to simplify the design. Your rocket engine's already making gas because of its staged combustion cycle. So use some of it, right? Instead of adding complexity to the vehicle like helium tanks. So, erudite, we needed that kind of explanation to bring everybody up to speed. If I'm just speaking random words, yeah, I get it. Sometimes you got to be straightforward with this stuff. Now, here's the thing. Let's think about here. Let's look at some Starship footage here. So, right now, the rocket engines, the 33 freaking Raptor engines, are pneumatically repressurizing the LOX and methane tanks right here. In fact, some of these lines that are going up the side of the booster are the same thing that you'd see on the external tank. They're pneumatic repressurization lines. Now, on the top of the methane tank, you have 4 valves. There's actually one there, and one there. So 12, 3, 6, and 9. around the tank. There's one right there, right? It's actually basically lined up with that vent right there. But see, now those are the RCS for super heavy, right? That's the RCS, but the reaction control system. The thing that it uses to basically steer the first stage around and come back down and land. Now, let's think about this for a second. This is actually an ingenious idea in more ways than one. Okay? So, I know what people are going to say. So, ullage gases are used for structural purposes. They're also used to make sure the tank stays at the right pressure, right? So, let's think for a second. Well, if you're using the ullage gases for your RCS, isn't the pressure going to drop inside of the methane tank? Well, yeah, that would be a good question if that's what you were thinking. Well, check this out. Let's think about it. When are those thrusters actually firing? So the thrusters are doing work right there. You just kind of can't see them. You can see some outgassing right there, right? When are those thrusters doing work? Erudite, those thrusters are doing work. You can see one of them's open right there. Well, I don't know why that one would be open. That might just be a reflection. But they're working right now to get the booster to flip combined with the gimbal action on Super Heavy because Raptors can turn in all different directions here. But if they were using those thrusters right now, the engines are on. So you don't have to worry about dropping the pressure inside of that tank because the engines are on. Right? So using the tank ullage for your RCS is actually super freaking smart as long as you're using it when the engines are running because of autogenous pressurization. The engine is still making gases, and now that the other engine's turned on, it's even easier. Right? So, where does that leave Super Heavy? Super Heavy is going to have to use some of those when the rocket engines aren't firing, right? But you don't really have to worry about an ullage pressure drop on Super Heavy when it's after Starship has separated. That's what my mind went to. Sorry, my mind's still kind of. You don't have to worry about structural integrity here because there's no upper stage attached to it, right? So you can take a little bit of a drop in pressure. So what about the propellant feed? Well, when Super Heavy is going to relight its engines to come down and land, you don't really, because you're decelerating, because you're getting aerodynamic deceleration, that's going to settle your propellants, and the propellants will feed correctly. So you can deal with having a little bit of a drop in ullage pressure from the thrusters, right? So, okay, what's the last part then? Well, the last part is Super Heavy coming down and getting grabbed by the chopsticks. Once again, with your ullage thrusters, you don't need to worry about it because your rocket engines are on. So you don't need to worry about a drop in ullage pressure there. Smart, huh? Like I'm telling you, genius. That's really, really smart. So what do I think about Super Heavy using ullage gases, using its own tank, like they're venting the gases out of the tank to steer that thing when the engines aren't on during its flight regime, or sometimes when the engines are on. What do I think about it? I think it's really freaking smart. That's really smart, man. Really good idea. Hey, Jeffrey, 73-month resub. Thank you. What's that? The indicator in question is... interesting. That's smart, Aqualux. Neat. Here you go. Trust me, bro. I see. I thought the pressure drop would be a bigger issue. Well, once again, the pressure is there for two reasons. The ullage gases are there for two reasons. One, it's structural integrity, right? That's a big one. Two, it's so you can fill the tank with something to get the proper feed.
Discovery,
right?
go at throttle up.
So you can get your propellant to feed into the engines correctly, right? But in the particular regime where Super Heavy is going to need to use its thrusters, right? Basically, when it's on its suborbital trajectory and it's turning to position the Raptor engines to come back down, right? You're going to see a depress in the ullage tank, but you don't have to worry about structure because there's nothing on top of it except for the hot staging ring and some grid fins. And Starship can basically stand up by itself. It's structurally integral. It can stand up by itself. Some rockets can't. Some rockets can't stand up unless the tanks are pressurized. Falcon 9. Falcon 9 would have a very, very hard time with a fully fueled second stage and well, not a fully fueled second stage. It would have a hard time with a first stage that's empty on top of a second stage and payload on top of it. It wouldn't be able to hold that up unless the tanks were pressurized. That's why Falcon has that transporter erector that holds it in position and lets go when the rocket's fully fueled, right? Can a first stage stand up by itself? Well, yeah, of course, but there's nothing on top of it, so you don't need to worry about it. That's why Falcon 9 can come back down and land, right? Now, once again, with Super Heavy, the parts where you're going to need those ullage gases for steering the thing, right, are going to drop the pressure inside of the methane tank, but you don't need to worry about structural, right? There's no second stage attached. No Starship on top of it, right? So the structure thing is not a concern. It's just the propellant feed. But you're going to get good propellant feed anyway to relight the engines because the rocket is decelerating against the atmosphere as it falls back down, right? So, yeah, you'd think the pressure drop is a big deal. No, not really. Mostly because of autogenous pressurization. Basically, when the rocket engines are firing, you don't need to worry about pressure. You don't need to worry about ullage gases dropping inside of the tank, right? Atlas, that's right, Tesseract. Atlas cannot, the older versions of Atlas, every version of Atlas up to 2AS, basically can't stand up by itself unless the tanks are pressurized. It'll fall over. It'll crumple like a soda can. Those are called balloon tanks. Yeah, balloon tanks. That's what they're called. Balloon tanks. And that is exactly what you think it is. You have to inflate your tanks to get the rocket to expand to be structurally integral. Centaur stages that fly on Atlas V right now utilize balloon tanks with a thermal protection system attached to the outside, like the foam on the shuttle's external tank, the orange foam. Centaur 3s and Vulcan on January 8th, Centaur 5s, those are using stainless steel balloon tanks. Centaur stages cannot stand up by themselves unless they're pressurized. They won't. They'll fall over. They'll collapse under their own weight. The pressure drop is an issue with the RC, with the reaction control thrust rocket guy, not structure on Starship, but also I don't think they use a blowdown system, so it's regulated, meaning constant pressure in the RCS to mitigate pressure drops and affects transients. It's not a big deal because the tanks are just going to repressurize. The propellant's going to settle because of deceleration, right? And when the rocket engines relight for the landing burn, the tanks will repressurize instantly, right? So if there was some type of pressure regulator in those valves, right, then yeah, I don't think it's a big deal. Simultaneously, rocket guys, do you think... I always was under the assumption that those valves on Super Heavy are basically directly into the tank. They go directly into the tank. Is it possible that those valves are using a tap-off straight from the autogenous pressurization? Is it possible that they're on a tap-off? Like, if the RCS is tapping off of the ullage propellants from the pneumatic repressurization lines, then you don't even have to worry about it. The Saturn V was able to stand up by itself? Yeah, Rob, it could. Mm-hmm. So could the space shuttle, yeah. Mm-hmm. How come balloon tanks don't crumble when the propellant goes low? Ullage. Tank ullage. So the solution there for tank ullage for something like a Centaur are helium tanks. The helium tanks are stored in what's called a composite overwrap pressure vessel hypersonic, or COPV for short. Give me 1 second. And Centaur, to simplify the design, has the helium tanks hanging off of the back. So, you notice there's a bunch of different tanks down here. What are these for? Well, one of them is Aerozine 50. So, a derivative of hydrazine. And that is a highly pressurized tank that's used for the thrusters. See those two little red caps right there? That's the RCS on Centaur, right? This one over here is helium tank ullage right here. And then right there, I'm pretty sure, if I'm wrong on this, let me know. I'm pretty sure that one is a helium tank that's designed to shoot high pressure helium inside of these inside of these two tanks here. Now, why would you do that? Well, these composite overwrap pressure vessels here can hold you can hold a lot of stuff in there at extremely high pressure, a lot of gas at really, 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 really high pressure. But like you said it, but what they do is they have a fuel bladder in there, okay? So basically think about like if you took a balloon and, you took the helium gas that's going to end up inside of the tanks, right? And you inflated the balloon inside of your pressure vessel with the gases that you're going to need for these tanks, right? Now, this helium tank here is basically attached to the bottom of the tank and pumps helium in between the balloon, right? And the helium with the balloon that's inside of there, it pumps helium into the balloon between the outside of the tank and, well, your fuel. It's called a bladder in aerospace engineering, and basically the gases that are being pumped in on the outside of the balloon inside of the pressure vessel squeeze the thing, and they use that to get the helium to go somewhere with pressure. Basically, kind of like your lungs almost. That's the diaphragm right there. The helium being shot in is the diaphragm, but that's not exactly like it, but it's the same idea. Basically, it breathes by squeezing the bladder. Yep. And then the Aerozine 50. My guess is that this this helium tank right here is probably tapped to both of those tanks. If I had to guess, that's a huge guess. I have no idea how Centaur is designed. I'm just looking at it. Okay. If you know, you probably wouldn't be able to tell me anyway. But see, there's a pneumatic line right there. See that little metal line? That's a pneumatic pressurization line. I'll bet you it's both of the ullage helium here and the thruster Aerozine 50 for the RCS. They're probably both tapped into the same helium tank, and they probably both have fuel bladders in them. Once again, huge guess. I'm just guessing with what I know. Mm-hmm. Yeah, nice Tesseract. There you go. I actually didn't think they used bladder tanks. I mean, Rocket Guy, you would have to use a bladder tank with the Aerozine 50, right? So once again, that's kind of me assuming. I could be wrong. It's rocket science. I understand it's more complicated than some bonehead on Twitch trying to figure out how it works, right? Like I get it, but I'm not really familiar with any other type of pressure actuation system that would work here. I'm sure there's something. I'm sure there's another way to do it. They could have the Aerozine 50 could be. They could just use residual pressure in the Aerozine 50 tank and have it go through a catalyst. That would make good monopropellant. That's good RCS. You could do that too. That would be that's another way. Basically, there are certain forms of monopropellant thrusters, guys, which are basically you have a tank and the tank is pressurized, and once the tank isn't pressurized, you're done, right? But the tank is pressurized into a pneumatic system, and attached to the end of the pneumatic system, right, this pneumatic tank system, there is basically a catalytic converter. Similar to a catalytic converter on your car. Same idea. It's called a catalyst, right? What does a catalytic converter do on a car? It uses precious metals to basically take some of the harmful gases that come out of an engine, right, and convert them basically into heat. That's why cats get so freaking hot if you're a car person. That's why they get hot, because the metal is reacting with the gas and it's making heat. That works really well to make monopropellant thrusters. You take something like Aerozine 50 and you shoot it through a catalyst, it's going to create heat, and that heat, that outgassing, will create thrust. That's how monopropellant systems work on satellites or on Centaur stages. That's another way that they could do it. They could just work off residual tank pressure. But Rocket Guy, what I'm looking at here, dude, is that this tank has multiple pneumatic inlets or outlets. There's multiple lines going into it. If it was just using the residual COPV tank pressure, there wouldn't be 2 pneumatic lines going into it. So that suggests fuel bladder. Could be wrong, though. Same with this thing. There's one there and there's one there. See what I'm talking about? 1 and 2. 1 and 2. So that doesn't suggest residual pressure. But the other thing is that you could use a helium bladder with Aerozine 50 to shoot Aerozine 50 through a catalyst. That you could. Absolutely. So, yeah, I mean, Centaur, how does it work hypersonic? The tanks are basically hanging off the back with the rocket engine. That's where I put RCS on my stages in Kerbal, like this, because, yeah, we can't put tanks inside of tanks and have Kerbal understand correctly what's going on. So I put the tanks off the back where they're inside of a inner stage that I would make out of a fairing, right? And because it's inside of a fairing at launch, right, these things will be aerodynamically occluded until the vehicle separates. At which case, Kerbal might not understand that they've separated from the vehicle, but if your stage is separating, you're already up in the vacuum anyway, so we don't need to worry about aerodynamics. Wouldn't that indicate hypergolic and not monopropellant? Why would you want your hypergolic fuel and oxidizer going into a fuel tank? Magisterks. I mean, it's possible, sure. But why would you want that? I don't want my hypergolic fuels combining inside of a fuel tank. That's a bad idea. The balloon could pop. 2 tanks? Oh, yeah. I mean, that's also possible too. It could be that. Yeah, but I'm pretty sure Centaur uses Aerozine 50 monopropellant with a catalyst. I'm pretty sure. But I know it uses Aerozine 50 somewhere. So maybe, I mean, Aerozine 50 can be used as a hypergolic propellant. It could be. Like, once again, that was just me guessing. I don't know that much about Centaur stages because there's not that much information out there about them. Oh, you meant for the RCS. I thought you meant for the helium tank itself. Yes, the hydrogen tank is a bladder. Yeah, cool. Well, I don't know, man. The ullage tank, I know. So, like, here's my thought process. That's definitely the ullage tank. Abso-freaking-lutely. It's definitely it. Now, another setup that they could have, Magisterks, if we're thinking what you're thinking, that could be NTO and that could be MMH, and you could have hypergolics going on here. But the plumbing for the thrusters suggests monopropellant because there's one fuel line going to the thruster block, right? So that suggests monopropellant with a catalyst, right? There would be 2 fuel lines going here. You don't want to combine your hypergolic propellants before they go into the rocket engine, right? Before you go into your thruster. You'd get an explosion in the fuel line instead of in the rocket engine. Right now, keep in mind this Centaur could be not finished. There's clearly some parts missing. That's possible. So, that could be a helium tank that's feeding the Aerozine 50 and feeding the ullage tank. Now, the question is there a bladder in here? I don't know. Maybe? I mean, Rocket Guy, now that I'm really thinking about it, dude, I think you might be right. I mean, not that I wouldn't doubt your judgment there. Because I've never heard, now that I'm thinking about it, in any of the aerospace textbooks I've ever heard, I've never heard of helium being used as a bladder to move more helium around. I've never heard of bladder tanks being used for a gas. So it's possible. It's possible that there's just a helium tap that feeds pressure and increases the pressure on this tank, and then they open up a valve. And if the regulated pressure between this tank and this tank is slightly higher than the regulated pressure that goes into the oxidizer and hydrogen tank for ullage, then yeah, you'd get proper gas actuation. You'd get proper gas flow that way. You might not even need a bladder tank. That might be complicating it. I think you might be right now that I'm really thinking about it. Is that green on the tank an insulation blanket of sorts? Yes. Not really. Yeah. It's not really insulation. That's something that would get removed before flight, Hammer. That's more make sure that during integration this thing doesn't bang up against anything. It's more padding than anything. Make sure that doesn't bang up against anything because, pressurized COPV, probably not a good idea. And even if it wasn't pressurized at this point, if they pressurize it on the pad, COPVs don't like being dropped. That's not really good for them. That's not good for the bottle. If one strand of carbon fiber breaks on that COPV, you go to pressurize it, it'll explode. Yeah, it'll delaminate and just poof. Cool stuff nonetheless. Yeah, I mean, there could be a bunch of different systems down here. But yeah, hypersonic, that's the gist of it. Basically, the helium tank rides on the back next to the RL-10. And its method of actuation, I'm not 100% sure. But yeah, that's what all this stuff is down here. And then obviously that thing in the center makes fire come out the back. Yeah. Yeah, for a fuel tank to be able to hold, and so why is dropping a pressure vessel that's composite overwrap bad? So composite overwrap pressure vessels are like, it could be an aluminum or titanium metal tank, right? And then it's wrapped in carbon fiber. The reason why it's wrapped in carbon fiber is to, when you pressurize it, you're going to heat up the gas inside it, and the metal is going to absorb some heat and expand a little bit, and then it'll eventually break. The carbon fiber wrapped around the pressure vessel prevents that from happening. So you could store gases in a composite overwrap pressure vessel at an insanely high pressure, way more than what just a regular pressure vessel would have. Now, in order to get the tank kind of stable when it's pressurized at a crazy high pressure, you need to have uniform force pushing out, right? So, or when you have the tank at pressure, you have uniform force pushing out on all sides, right? If you have uniform force pushing out on all sides, you need a uniform tank wall, so to speak, on all sides. So if you drop it and you snap a strand, you're getting differential outward pressure here, and basically it's a chink in the armor, and it will end as badly as that does. Yeah, like if you play World of Tanks, that's like ammo racking somebody. Not good. Not great, Bob. It seems like the big bottle in the bottom of the Centaur holds the hydrazine propellant for the RCS. Mm-hmm. The weak link in a chain. Mm-hmm. Yeah, Thomas. Yeah, that's probably right. Once again, I was just guessing based off of what I saw here. Like, once again, keep in mind, I just play KSP. Okay, I just play KSP. It could be that's the helium tank, and that's the Aerozine tank, and that's your ullage tank. Like, it could be what you said. I mean, I always thought that actually, this tank being larger does make a lot more sense if it's for hydrazine, right? Because that would be holding liquid and these two would be holding gas. It does make more sense that way. Or that one be holding Aerozine 50, right? And like Thomas, if you're right, and I'm not saying you're wrong, like if you're right and that's the case, and this is your thruster propellant, right? That's the propellant, that's the Aerozine 50 going through the catalysts there. If that's correct, that means that this one or that one is tank ullage, right? And then that's your manner of actuation here.
that one's probably for ullage because 2 here. But also, one of these is going to need to lead to this one for the bladder tank. So I'm not sure. One of these tanks could be serving as an accumulator. Like I'm not 100% sure. I know the general principles of what's going on down here. I just don't know exactly what everything does. Yeah, Tesseract, yeah. The gist of it is don't drop it, right? But yeah, good talk about ullage. So the thing is that with going back to it, just kind of bringing this all back together with super heavy, you don't have to worry about that. No ullage tanks inside, no COPVs. It's stainless steel. It can stand up by itself. It can tank a little bit of a pressure drop, but what makes the most sense in my mind is not having the ullage thrusters vent directly to or go directly to the tank. They could be working off the autogenous pressurization tap off. And if that's the case, if they're connected directly to the tap off lines, so those lines would stay pretty highly pressurized basically until you vent them because the rocket engines are putting gas in there. So like, let's think in stationeers now. So you have a tap off getting methane gas and oxygen gas or gaseous oxygen out of these rocket engines. One of the repressed lines goes to the top of the LOX tank. The other one goes to the top of the methane tank. The one that goes to the top of the LOX tank, you don't want to depress that tank because there's a methane tank on top of it. So you need to maintain structural integrity there, right? So the methane gas goes all the way up to the top. So how do you do this? How would you do this? So you could have the ullage valve from the autogenous pressurization going in to the main tank volume, right? And have that be on a pressure regulator that's equivalent to the pressure that's needed for proper propellant feed. And then, so that's basically a check valve in there. That would be a good passive system. Basically, vent the pressure into the tank until the tank is at the right pressure, and then the valve passively closes when pressure equalizes, right? Or and then you pressurize the lines. You could have an accumulator up there at the top to pressurize the gaseous methane and use it for the thrusters. It's possible. That's a little complicated. The easy way to do it would just be to have the autogenous pressurization lines go right into the tank and then have the valves just on the outside. But you could have an accumulator in there to prevent ullage tank pressure drop. It's possible. Yeah, go ahead, Magiturks. Hypersonic, thank you for that tier 223. I appreciate it. And SpaceX usually tends to keep things simple. So, Rocket Guy, if you're still here, if I may pick your brain for a second, what would be let's just play off the notion that the AP line just goes right in. It goes right into the main tank volume. How would you manage your ullage propellant pressure if you're using your ullage propellants for RCS? Ooh, NTRS, my favorite. Centaur Propulsion Systems. Appreciate the enormous amount of knowledge I gain here. Yeah, I try. This is an older Centaur. That's a Titan 3 Centaur right there. It's a 1973 outdated document. It is, but it shows a bit. So, yeah, see? Fuel is stored in the balls right there. Centaur's got balls. Yeah, this is for a dual engine Centaur, a DC. Modify, here, hold on. Engine cluster manifold assembly, 2 axial, 2 lateral. Engine cluster manifold main assembly, LH2 boost pump. Okay, booster feed valve. Hydrogen peroxide. Interesting. But it illustrates what you're demonstrating. Yeah. Yeah, oh yeah, oh yeah. Hey, Raptic. Thank you for the bits, man. 3,333 bits. Thanks, buddy. Ha, very nice. Here we go. Yeah, Magistrix, I got you. Thanks for looking for it. So the reaction control systems. Oh, okay. Boost pressure bottle. AC. What the heck's AC? Yeah, see, check it out. Those are bladder tanks. See, it says HE and then hydrogen peroxide right there, H2O2. And see these weird lines? There are bladder tanks. Hey, Brian. What's going on, buddy? Yeah. Yeah, those are bladder tanks. Oh, that's really smart, man. If I'm looking at this right, I think those are catalysts. I think. Is there like a diagram here that I can look at? Let's see. The box with the X in it. Doing well, my man. Hope you too. Yeah, I can't complain, man. Can't complain. Okay, Rick, you have a KSP2 question. Fire away, dude. Have you had issues with docking ports not redocking after you separated them? Yes. So these older versions of Centaurs are using hydrogen peroxide for their hydrogen peroxide with what looks like a catalyst. Hey, condition 48-month resub. Oh, good. It's Funkin'. What's going on, man? How you doing? Yeah, see. H2O2 vent. H2O2 vent. Yeah, see. Hydrogen peroxide is being combined with helium. And that uses an LH2 boost pump. Oh. Hypersonic, those tanks aren't just there for ullage and thrusters. They're not just there for that. They use... Well, I don't know if they're still using hydrogen peroxide. I'm pretty sure it's Aerozine 50, which is different. Yeah, but the hydrogen boost pump.
Discovery, go at throttle up.
So they use some of the pressure here to start spinning a pump to feed the RL-10's expander cycle. Yeah, it's basically a primer. They're using the hydrogen peroxide in this design as a primer to prime the for the boost pump. If I'm looking at this right. Because in order to start an RL-10 engine, you need to start the flow of hydrogen, right? And you could do that by just opening a valve between the tank and the engine and letting the propellant, using the pressure of the tank, go into the rocket engine. Sure, you could do that. But now you have to worry about that same problem. How do you get gases back inside of the tank? Right? You got to worry about tank ullage, because if the pressure drops inside of a Centaur, your structural integrity goes to crap, and the rocket engine pushing on the bottom will crumple your fuel tank. Don't want that. So they're using the hydrogen peroxide in this design through a catalyst to actuate a pump that starts feeding hydrogen propellant in to restart the RL-10, from what I can tell. So like I said, we have a mystery as to the present hardware layout, but it shows what you were talking about in schematics. Yeah, once again, it's probably not hydrogen peroxide. I'll bet you they found something better. Helium, Aerozine 50, hydrazine. There's probably better things than H2O2. The reason why H2O2 decomposes over time. I think. I'm pretty sure. Chemists, hydrogen peroxide is not stable. It decomposes over time, correct? I only know a bit about the Centaur because of an astro photo, because the servo actuator uses a harmonic drive. Oh, you use one to guide your telescope. Cool. H2O2 decomposes over time. 6 months shelf life. There you go. Yeah, cool. it'll decompose into water, right? Yeah. Hydrogen peroxide also can be used in a monopropellant catalyst design, guys, so that makes more sense. It looks like they started with hydrogen peroxide on these early dual-engine Centaurs. So this would have been a Centaur design from the 60s, like late 60s here. The higher the concentration, the faster. Yeah, water and O2. Yeah, I got you. Water. Yeah, they use that to start the. They're basically using that LH2 boost pump as the. So, guys, like Falcon 9 with its Merlin engines uses triethyl aluminum and triethyl borane to actuate the gas generator to start pumping fuel. With the RL-10, you don't have a gas generator, it's an expander cycle. So all you got to do is start moving propellants in through the cooling channels on the nozzle, right? And it will heat up the hydrogen enough into gas to start turning the turbines on an RL-10 to start the fuel pump actuation. Limits the lifetime on Soyuz for the same reason. Yeah, John, I'm pretty sure the capsule environmental control and life support systems are using hydrogen peroxide for simplicity of design. Without the service module, right? Yeah, your life support systems are limited to not very long. And yeah, that's the bottleneck for Soyuz. That's why you can't, Soyuzes can only stay up there for, 4 to 5 months. Thanks, Magisterks. Thomas, you have a newer one here. Let's take a look. I miss doing this, guys. I miss going and reading about this stuff. Another fun fact, whatever the application, ullage or inerting for hydrogen, nitrogen or argon is never used. Creates corrosive compounds. Chemists, please confirm helium is preferred. Yeah, Magisterix, I wouldn't use that because they're higher mass. They have a higher atomic mass. The atomic mass is higher. The less rocket you have on your rocket, the more fuel you have on your rocket, the further you go, right? Like, did KSB1 ever update to make the aero parts like nose cones useful? The last I played, they didn't do anything. I usually make parts like that out of fairings and stuff, Tesseract. Oh, boy. End of page 10, the beginning of page 11 talks about the new reaction control system on Centaur 3. The RCS has been significantly upgraded for the common Centaur. The stretch to the tank required additional force for vehicle control, so the lateral thrusters were upgraded from 6 to 9 pounds of thrust. A newly designed large composite wrap... N2H4? Has been developed with the capacity of 340 pounds, twice the capacity of the previous bottle. It will accommodate all known mission requirements and weighs less than the 2 bottles previously required for some missions. This large bottle will be cut in for Atlas V use on the second Atlas V vehicle. An integrated reaction control system pyro service valve was developed and located on the bottle yoke for enhanced thermal control. It provides parallel redundant pyro valves, a service valve upstream and downstream of the pyro valves, and a pressure transducer all in one compact unit. It also increased the system flow area It also increased the system flow area and eliminated 55% of the RCS welds for improved reliability. Improvements to the pneumatic system were performed on the propellant tank pressurization, the tank vent, and gas detection systems. Yeah, N2H4. Yeah, hydrazine. Yeah, cool. The tank pressurization system on the common Centaur consists of 3 composite-wrapped 26-inch helium storage spheres connected to the propellant tanks through the new single pneumatics panel. 2 of the helium bottle locations are common between the single and dual engine common Centaurs, and the third is unique. A fourth helium bottle kit is available to support 3 burn mission profiles. The revolutionary single pneumatics panel design combines the hardware that was previously located on 5 separate panels into a single panel. The panel is built and bench level tested before installation on the vehicle, greatly simplifying the final assembly process. Wait, hold on, let me read that one more time. 2 of the helium bottle locations are common between single and dual engine Centaurs. Consists of 3 composite wrapped 26-inch helium storage spheres connected to the propellant tanks through the new single pneumatics panel. The non-reversible tremor pipe to the differential girdle spring on the up end of the Grammys. Yeah, the spherical ones. Yeah, okay, cool. We got it. Spherical ones are helium. Hydrazine is in the long tank. Yep. That's used. So, from what we can tell, the helium tanks here are used for the LH2 boost pump, tank gullage, and to actuate the monopropellant systems, I think. How do they handle side fumbling? Retroencabulation. Yep. Not to be confused with long drain. Yeah. Of course. Oh, look at that. Spark igniter. You see that thing right there? That's a very, very, very expensive aerospace grade spark plug. Yep. Super cool space spark plug. I wonder if it uses points ignition. The older ones might. Everybody that likes old cars is like, yeah. Everybody else is like, what the f are you talking about, man? Yeah, cool. Oh. The only thing that I'm really kind of losing track of, I don't know what a pyro service valve is. My guess is that that's some type of valve that's used to vent the tanks for safing, but I could be wrong. Yeah. Cool. But can you guys see why SpaceX was looking to get rid of all this? That's where you mix the propellants for RCS. Interesting. Can you see why SpaceX is looking to eliminate all that? Falcon 9 uses something kind of similar to that. But I'm pretty sure Falcon 9 uses nitrogen for its reaction control systems on the second stage. That similar system that is on the first stage, I think. I don't know. There's not much documentation on that thing. A pyro valve is lightweight and reliable. These valves are critical to the liquid and gaseous fluid systems of missiles, launch vehicles, spacecraft, and undersea vehicles. Often initiated by a NASA standard initiator, our space standard initiator. Such as our space standard initiator. These explosively actuated valves perform the same function as valves by other means. The difference is that the operation of the explosively actuated valve is performed by a pressure cartridge, initiator, or detonator. The advantages in the use of explosive as valve operations are twofold. First, the large energy conversion ratio, the long-term storage, and the high reliability of the explosive device. Second, the rapid functioning times in milliseconds, which are available in no other type of valve. They can be designed in a wide range of sizes, configurations, and fluid mediums, including normally open, normally closed, and multiple valve combinations to successfully support your mission-critical fluid systems from deep sea to deep space. Hey, that's what I said. Fire service meaning explosively actuated. Yeah.
Interesting. When he wanted to stay closed for ages until it must stay open. I mean, can't have any valve if you blow the dang valve up. It's a good way to make sure that your valve works. The only thing is that it's a one-time use valve. You know what I mean? It survives the charge. Can we just bask in the idea that we have a one-time use, one-stroke engine for use as a valve?
Yeah, I guess they actuate super quickly because if you have a valve that's riding the detonation wave, right, it's going to open really quick. If it's detonating, they said they had detonator valves. If it's detonating, that means the pressure wave from the initial actuation is going faster than the speed of sound. So long story short, that valve opens really quick. Yeah, really fast. Yeah. Yeah. Oh, we need to make the valve to open faster. Why not blow it up? By God, I think he's got it. Fun fact, that's how seatbelt pretensioners work in every car. Explosions? Could it be using the hydrogen to create an explosion? Well, it's cartridge-based, Geek, is what they said. So there might be. You could use anything that's going to create a nice explosion. You could use hypergalls. You could use T-tab. It depends on what you're actuating. You could use a bunch of things.
Discovery, go at throttle up.
You could use anything. Hey, oh no, 42 months. Send it. When the airbag goes off, an explosive goes off in the seatbelt buckle or retractor. It pulls your seatbelt tight. Oh, interesting. Pyro valves. Yeah, if you use springs. Yeah, well, it's funny because, Geek and Elvis, you guys are talking about car engines, right? If you have a spring-actuated valve, right? If you need it to open faster, you'll literally get the valve equivalent, the aerospace valve equivalent of valve float. Basically, valve float happens when a car engine is at super high RPM, and the rebound on the springs can't actuate the valves fast enough. Basically, the piston goes up and down 4 times in the time that the valve can only open twice, because how the valve opens is basically a rocker pushes the valve down, right? And it compresses a spring, and the spring pushes the valve closed, right? On a car. And when the spring can't rebound the valve fast enough, the valve will basically just sit there floating between the open and closed position, hence valve float. Cool. Interesting. Get rid of springs like Formula 1 did and get 20,000 RPM. Yeah, Formula 1 cars have a pneumatic valve systems to eliminate that exact problem. See, this stuff's all connected, dudes. This is why I like doing this. This is why I miss doing this. It's all connected. Physics is physics. It doesn't matter if you're flying into space or on a Formula 1 car. Physics, engineering is engineering. This all kind of ties together, which is super freaking cool. I think that's really, really interesting. Yeah, the free valve. Yeah, free valve uses a pneumatic actuation, Hellfish. Yeah, that's what Koenigsegg free valves are. Oh yeah, Goalie, your video here. Let me see. Yeah, this is Goalie's video of the launch. Let's take a look-see. Yeah, the Tesla valve. Passive one-way valves. Smart, using with fluids. Yeah, those are really smart, weather guy. Also, I'm about to get railed by a nor'easter, aren't I? High def. Okay. Gwen has started using Twitter. Uh-oh. Ah, cool. Should start hearing the noise here in about 10 seconds. Great shot, goalie. Actually, how far are you away? I thought you'd get the sound by now. I haven't been tuned in much. You want me to take a look? Nah. Nah, I know we're gonna get dumped on with a snowstorm. Hopefully, because I'm close to the ocean, we don't get wrecked. You were at the boat ramp at Port St. John. Okay, so you're a little ways away. You're probably not going to hear the sound. Yeah, that's... There you go. It's faint, but you can hear it. Is that Ian? Yeah, I'm hearing Ian. Hope the snow doesn't impact your commute to work. Yeah, me neither. There's Miko. Stage separation. Now watch, the first stage will flip up this way. There's second upper stage ignition. Right there. And boost back. Oh! How the heck did you get this footage, man? How'd you do this? What? Dude, that's fantastic. Yes. That's sick, dude. Dude, that first stage is like 120 miles away. What the actual frick, dude? That's a long way. What's that, Doom? Yeah. Is that Guess Who, but with airplanes? Oh, I don't hate that. Great track, dude. Oh, there's the nitrogen. Nitrogen gas thrusters. Yeah, see? Up there, there's no ambient pressure, so the gas is kind of able to freely move away from the vehicle, basically at the velocity that it shoots out the nozzle at. It doesn't stop, that's why it just kind of keeps going. Oh, that's cool. Those are those types of thrusters that we were just talking about. Well, similar. They don't use hydrazine. That's nitrogen. The cold atmosphere might be useful for less atmospheric distortion. Yeah, that's right, Jack. That's a good point. This is a pretty damn good track, dude. What was that? Dodge. Dodge. All black Dodge Ram. That was a Dodge Ram. The 5.7 starter is very distinct. The Toyota, I heard a valve knock. At least that's my guess. I don't know what it is. I was trying to be funny. Yeah. So check this out. What those thrusters are doing, they're slowly turning Falcon 9 around. So when Falcon 9 completes its boost back burn relative to the ground, so it's going this way, and then it does the boost back burn, right? And then they're slowly turning it this way. You don't want to use the RCS to turn it too fast, because then the propellants will slosh around inside. So if you notice, they're just kind of every once in a while, and they're basically turning the booster.
Discovery, go at throttle.
So the engines are going to be facing the... they're going to be facing into the windward side. So basically, the engines are going to be flying business end first. You need a model to explain it.
Oh, it's coming down.
Oh, it's coming. Basically, the thrusters up here, right, are... When it's done with its boost back, it's like this. And then the thrusters are slowly moving it in this direction to get it ready for what you're about to see right here. It couldn't be a ram. You would hear the wind whistling through the rust holes in the fenders. It's Florida. Huh. Yeah, supersonic retro propulsion. I'm a fan of this. Can I just... You guys mind if I just... Just give me a second. Yeah. Hey, Asmalak. That's the heat shield, man. The rocket exhaust is being used as a heat shield. If we back it up a little bit. See it? Notice how it's heat shield shaped? It's curved. See how the flames are curving? The flames are curving around a bow shock right there. You can't really see it, right? But you can see the shape of it. Isn't that cool? This is great, goalie. Really, really good, man. Hold on. Let me back it up again. You see? Look at the shape. Shaped like a heat shield. Like a little bit of a cone shape. Or not a cone shape, a little bit of a hemispherical shape. Yeah, Caviar. Return to launch site. Yeah. That's wild, dude. And then the reason why they changed shape one last time is because so they fire one engine and then they turn 3 on and then they shut 2 off. Where are you? Go back when the engine goes down at us. All right, let me see.
Oh, it's coming down.
Oh, it's coming. So... Oh, it's coming down. Let me look slow. I'm still it's kind of impressive that you could still see this thing. I mean, this is a long way away. Actually, I was going to say, what was booster average? Booster average is about 120 kilometers per the SpaceX cast. And that thing's downrange a good deal. It's got to be 120 miles at least. That's a long freaking way. That was RCS. Shut off the wrong 2 engines. I do what I want. Nice. 1 engine. Oh, hang on. Back it up a little bit. Yeah, Madge, for sure. 1 engine, 3 engines. That doesn't suck, dudes. I didn't see any plasma, dude. I saw it was all RCS. We didn't see plasma on the cast until right before the burn. Alright, let's get to the landing. Street light. Landing burn. Power lines. Dogs. Landing leg deploy. Yeah, I went over the horizon. Yeah, goalie's a little bit of a... He's a little ways away in this shot. That's why we didn't hear it. That was definitely a 2.7 Tacoma. That second one, yeah, for sure. Can you hear the booms? It's gonna take a second for the sonic booms to get out here, but you'll hear it. It'll be a thump. Give it a second, Ryan. Dags, you like Dags? Wait for it. Nope, guess not. Great track, goalie. Yeah, where the heck are they? I missed it? Oh yeah, yeah. That was in fact them. Yep. Like, yeah, at this distance, like I said, it'd be a thump. It wouldn't be a crack. Yep. 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 Oh yeah. Yeah, it took a second. Come on, voice. Come on, voice. Let's go. There we go. All right. So, here, let's see something. Let's see if this old trick works. So, the sonic booms would have happened somewhere around here, right? Let's just say they happened to, you know, that's when the vehicle went transonic right before landing, right? So, no, that's got to be 43 seconds. No, can't be. You can't be that far away. Yeah, Brian, sonic booms sound like a cannon going off, yeah. So you hear the sonic boom about 40 seconds after the booster lands. Yeah, you're a long way away. Here's the better booms for your videos. Okay. If this doesn't cooperate, guys, we're gonna pack it in. Voice is not doing good. All right, let's see, goalie. This might get loud. Nice. Nice. The car alarm's real? Oh, yeah. Watch the video. You can see the sound wave. What sounded like a bottle rocket going off there? That's funny. Yeah, look at that thing. That's a really steep landing trajectory. It's the VAB, yeah. Nice. Suffering from constipation? Stand near a sonic boom. Stuff will come out. Yep. Yep. Well, hey. Ended up doing more space news. All right, but it's only 8 o'clock, so we got. Let's keep going. Oh yeah. Let's see this. Let's see what we got. 2024 is off to a roaring start with the launch of Starlink. This is Gwen Shotwell. She's the president of SpaceX. And our first direct-to-cell services yesterday. I also must congratulate the extraordinary SpaceX team for a record-breaking 2023, shattering global launch records, flying more people from more countries to orbit, completing 2 very exciting flight tests of Starship, and growing Starlink's impact by more than 1.3 million new customers. These achievements would not have been possible without their dedication and determination to overall greatness. The flash hits right as the sound of the booms. Nice. Cool. So no car stream? I don't know, dudes. Starship Ship 30 is being cryo tested right now. Jeez. Man, that's quick. All right. Go gargle some lemon juice and honey and get some rest. Yeah, I'm kind of... I hate, guys, like, it's killing me. It's killing me streaming for 8-9 hours. Like, I don't... It's really pissing me off. I'm playing around with a mod for a certain blue rocket in anticipation of its first flight this year. About cars, just might gut your kid a 5-cylinder Volvo. Yeah, nice. Oh, Thomas, that looks good, man. Very nice. Breaks are important. I just took a break. Dang it. Yeah, guys, you know what? It's probably better. I'll take it easy here. I got so much stuff to do. What do you guys thinking for tomorrow? What do you think? Would you play Kerbal? Could play Kerbal. Play Cities. I'm just like with Cities, I'm just kind of running out of things to do. That's all. Like we pushed the city to maximum capacity and kind of went from there. I mean, I'm sure I could think of something. KSP1 Fun Day. Yeah, yeah, exactly. I kind of think we should wait for an update. Sorry if I'm a bit spammy. These things are right up my alley. I imagine. I don't care. Doesn't bother me. I told you. Talk to your will's content, dude. Keep going. That's the kind of stuff I want in my chat. What is this erudite? Oh, neat. That's cool. Neato. That's pretty neat. Just build in the starting tile and see how big you can hit the pop in a single starting tile. Have OKSP1 and blow stuff up. I don't know. We'll think about it. Yeah, Caviar, it's possible. Ooh. Could play Hearts tomorrow. How about some Satisfactory? Maybe. All right, I'll think about it, guys. I'll have something for you tomorrow, okay? I'm just going to make sure that I'm not pushing myself, dude, because I don't... Something's wrong. I got another sickness. Just when I got over the last frickin' one.
Discovery, go at throttle up.
Hey, Starshot, 31-month resub. Adios. All right, let's see who we can raid, dudes. Take it easy, man. Yeah. I said I would hit my A game in 2024, and yeah, this is a great start. 2 freaking 8-hour streams back to back. Lovely. That's poo-poo. That's poo-poo. Doo-doo caca poo-poo. It's not good. Underperformance is bad. You got the cooties. Yeah. Why did it have to be a respiratory? Why does it have to be a respiratory thing going around? The one thing that I freaking need my freaking voice. This is ridiculous. All right, guys. There's not many others around. Let's go see what Etal's up to. Would you rather be sitting on a bucket? I mean, at least that gets out of your system real quick. But anyway, guys, let's go see what Etal's up to. I'm sorry about the short streams. I know people are like, oh, sorry about the short